Hi, welcome to this question on Euclidean geometry, similarity and congruency. Let's have a look at question 3. We're given AC is a diameter of circle ADC, and we're also told that DB is perpendicular to that diameter AC. We're also given that the length AC, so this total length here, is D units. AD is given as C units, which is over here. DC is given as A units, and dB is given as H units. Okay, so the first thing they've asked us to prove that H is equal to AC over D. So immediately when I see something is equal to a fraction, which brings to my mind ratios, an easy way to show it is to try find similar triangles or congruent triangles and then use the proportion part of similar or congruent triangles. So congruency would show sides are equal in length. Because we have a proportion here or a ratio, I'm most likely going to show two triangles are similar and therefore try and achieve this here. So what I'm going to do is I'm going to divide both sides by C. I could have also divided both sides by A and we could have done a similar logical flow, but in this case I'm just going to divide by C first. Okay, so this statement is true if and only if H divided by C is the same as A divided by D. Okay, so that's a true statement because if I cross multiply both sides by C, I get back to that original equation. Okay, so now let's see what two triangles have these lengths here, and this will give us the clue of which two triangles to prove are similar. So H and C are in this triangle ADB here, which is a right angle triangle, and then A and D are in this bigger triangle ADC. Okay, so if I look at triangle ADB, there's a 90-degree here. So if I can show another 90-degree in that bigger triangle, that'll help me because I have two angles that are equal. But we know that AC is a diameter. Okay, so I'm going to start off my proof by observing the following. If AC is a diameter, then this must imply that angle ADC is 90 degrees. And the reason for that is angles in semicircle. Okay, so this entire angle here is 90 degrees. So if I pull out that triangle, all right, so ADC, that's a right angle. That's D units, that's A units, and that's C units. Okay, and then if I look at this triangle here, ADB, there's the right angle at B, D, and A. Now, AD here is C units, DB is H units. Okay, I don't know the length of AB just yet. Okay, so let's see if we can prove that these two triangles are similar, and then we can figure out that if we do H divided by C, we hopefully get A divided by D coming out of that, all right? So whatever you're trying to prove is sort of the motivation of trying to show you what you need to prove are similar triangles. Okay, now I'm going to note that this angle A here is equal to itself, common angles, right? So if I have a 90-degree and a common angle on both, right? Therefore, by angles in triangle, this angle here must be equal to that angle here. So I have three angles that are equal to each other. All right, so let's note that. So I'll say consider triangle, and I want to do it in the order that I want to show is actually similar. So I'm going to go from the dot to the other angle to the right angle. So ADB and triangle. So from the dot to the other angle to the 90-degree, that's ACD. Then we can note the following. Angle A is equal to itself. That's because it's a common angle. All right, so I've shown that these two angles are equal. I've also shown that DBA is equal to ADC, which are both 90 degrees. Okay, so the DBA comes from the fact that DB is perpendicular to AC, and the other one comes from angles in semicircle. Okay, so therefore that means the leftover angle ADB must be equal to the leftover angle ACD, and that's by sum of angles in triangle. Okay, so therefore what have I shown? Angle A equals angle A, angle B equals angle D here, and angle D here equals angle C here. So therefore triangle ADB is similar to triangle ACD by angle, angle, angle. Okay, great. So that means side lengths in the same correspondence must be in the same proportion. So if I look at dB, right, over AD, that must be in the same ratio as DC over AC. So therefore I have dB over AD equals DC over AC by similarity. dB was H, AD was C, DC was A, and AC was D. Look at that. We've exactly proven what we wanted to show. So if I cross multiply both sides by C, I get exactly the desired result. All right, so again, whenever you ask to prove something, try get it into a ratio, identify where those side lengths come from in each triangle, and then work your way to proving that those two triangles are indeed similar to be able to get that result. So you're sort of reverse engineering, right? And then lastly, given that same criteria setup, we want to prove that 1 over h squared equals 1 over a squared plus 1 over c squared. Now this almost looks like the Pythagorean theorem, just upside down, right? A sort of reciprocal Pythagorean theorem, if you will. Okay, and that's no accident or coincidence. Because it almost looks like a Pythagorean theorem, that probably means that we can use the Pythagorean theorem in one of those 90-degree triangles to try and work this out. So again, just like the previous question, what I'm going to do is I'm going to try and simplify this expression to something that looks a bit more what I'm used to seeing, and then work my way from there. So what I'm going to do is I'm going to keep the left-hand side the same, and because I'm adding fraction with different denominators, I need a LCD. So my LCD is the product of those two denominators, a squared times c squared. So I must multiply c squared here and a squared here, and I'm adding the two. Okay, so this is equal to a squared plus c squared all over a squared times c squared. All right, and that's 1 over h squared. So what I'm going to do is from here, I'm going to further simplify it and multiply both sides by a squared c squared. So that's going to be a squared c squared over h squared equals a squared plus c squared. Okay, so we're getting a bit more simplified here now. Immediately, so I know that side length is d. If you look in this big triangle ADC, which is a 90-degree triangle, a squared plus c squared by Pythagoras must be d squared, right? So that's sort of helping us, all right? And then this a times c over h, where does that look familiar? Well, look at the previous question. We have h equals ac over d. H equals ac over d. So let's go ahead and prove this. So what I'm going to show, so if I write this expression out here, a squared times c squared over h squared, if I write that expression and simplify it, if I get a squared plus c squared, then we're done. So what I've done is I've algebraically manipulated this equality to show that it's equivalent to showing this equality. So if we can show this equality, then we are done. So essentially you're proving an identity, like a trig identity, but an algebraic identity. So if I can show that this left-hand side is equal to the right-hand side, then it's the same as showing this expression here. So that's the technique I'm using. Okay, so that's going to be a squared times c squared over. Now, we've just proven that h equals ac over d. That's what we've just proven. And again, like I told you when it comes to geometry, whatever you prove is usually going to be used somewhere else in the calculation. Okay, so I'm going to substitute ac over d, and remember we're squaring it. So I have a squared times c squared all over. So if I square that out, it's going to be a squared times c squared over d squared. So when you divide by a fraction, you multiply by the reciprocal. So it's a squared c squared times d squared over a squared c squared. Okay, so the a squareds will divide, the c squareds will divide, and you're left with d squared. Okay, but d squared in this larger triangle by Pythagoras is a squared plus c squared. So that's by Pythag. So we've successfully proven the identity. The left-hand side, so the left-hand side is equal to the right-hand side. And because we've shown this equality is true, this is true if and only if this equality is true. Okay, so you see how we spun it around. We made this equality look like something more manageable, and we've shown a new equation that is true if this original equation is true. So all I've done is proven this equation star here by using the left-hand side, simplifying it down to show that it's actually equal to the right-hand side. And because that equation star is true, that means this original equation is also true, because all I did was algebraically manipulate that original equation to look like this one in star. They're exactly the same equation. The structure might look a little bit different, but algebraically, they're exactly the same expression. All right, so that is how we would do this type of question. I'll see you in the next one.